Hello, everyone. It's me, Dr. V. Feel free to call me Terry. It's good to hear from you guys. Hope you're all doing well. Hope you guys are taking care of everything. As some of you may know or not know, I'm still in Alexandria, Virginia. I work in Washington, D.C. Teaching's going very well. I do miss working with you guys. I'm proud to admit that. I'm freely admit that you definitely were a group of students that I liked working with. But you guys are now taking organic chemistry, so I'm here to help you with this. So hopefully it goes well. As a reminder, your professor, Dr. I believe Jennifer, I forget who your professor is, but always go with what she tells you. So she is going to be your main person. Um, we should agree on everything, right? Because it's chemistry. But if we ever say anything that maybe contradicts slightly, go with what she says just because she's the one in charge of the class. I am here to help you and to give you these small little areas of reinforcement, help you really catch on to what, give you a good idea what's going on. But basically, the main idea is just for me to reinforce ideas. And then you guys can come to me with questions if you're unsure about particular topics, and I can expand on it and help you understand it. So I'm just going to go through this week one PowerPoint, and I'll upload it to YouTube, which is where you're most likely watching it now. So the important thing is to understand what these questions are asking, and I'll break them down and help show you how to get the answer. So let's go ahead. So what is in the bubbles of pure boiling water? So it says here, and so the idea, right, is if you take water and you watch it boil, eventually you will start seeing bubbles form. And don't forget, when we boil water, that means we are taking water from its liquid form and putting in enough energy to turn to its gas form. So as we go from solid to liquid, as we go from liquid then to gas, right, we are turning the water molecules into gaseous form, and those are the bubbles we are seeing. So water will still stay together, right? We're not putting in enough energy to break the bonds, but it should, we're going to do a phase change. All right, so drawing organic structures 101. So one of the things that we're going to focus on in organic chemistry is that when you look at organic chemistry, it's the chemistry of carbon. And as we look at more and more complex molecules, you're going to have to know how to draw them in a simpler way because compounds can get very out of hand very quickly. And so you're going to see why the new structures we're going to show you how to do, why drawing it this way is going to save you a lot of time. Sorry, just took a drink of Coke. And so you need to understand how this works. And so here's our wonderful periodic table. And of course, you guys know all this very well. And what we need to know from this periodic table is basically the following, as I go and click on, is that we need to understand the hybridization or the electron configuration of these common elements. Because in organic chemistry, carbon is our sole focus, but we also do care about these other elements. These elements will pop up in the course of our organic chemistry. Nitrogen, oxygen are very important, fluorine and chlorine, bromine, iodine, they're not shown here, but they're there. Hydrogen is very common, boron, phosphorus, and so these are very important. So what we need to know now is how many valence electrons do each of these elements have, right? And so the main block elements, when we go through them, basically all of these are going to have what we're looking for. So how many valence electrons does carbon have? So if we go back a slide, we just count left to right. 1, 2, 3, 4. So carbon has 4 valence electrons. It has S2 and P2. Silicon, which is right below, would also have 4 valence electrons. So you just basically count 1, 2, 3, 4. And as you get more practice doing these types of problems, it's going to become second nature. Because if someone asks me, hey, Dr. V, how many valence electrons does a halogen have? Well, I know 1, 2, 3, 4, 5, 6, 7, right? All halogens have 7 valence electrons. So as I said, as you practice, as you do more of these, it's going to be more common. It's just going to make more sense, and it's going to be second nature to you. But the main idea is just practice and looking at these. All right. So the answer should be B, 4. How many valence electrons does bromine have? And we just did that. It's a halogen. If I count from left to right, it's going to have 7. How many bonds does nitrogen make? Well, this is going to be a little bit of a trickier one. But when we draw our bonds, basically, right, if we're thinking about how many bonds does it want to make, nitrogen, if you remember, likes to make 3 bonds, right? It can make 4, but it prefers 3. Right, next up is how many total valence electrons does CH4 have? So in order to figure this out, all you do is you add up the valence electrons for each of the elements. Carbon has 4. Hydrogen has 1, so you have 4 total. So carbon 4 plus each hydrogen is 4 more. So you should have a total of 8, right? And so you basically, if you want to find out total valence electrons for a compound, just add up the number of valence electrons per each element, all right? Next up. So Lewis structures. This is something we talked about when I was your instructor, so hopefully you guys remember this. First, we count the valence electrons in the molecule. So basically like we just did, we just added up the 4 for carbon and 1 for each hydrogen, right? And then we're going to, for every negative, if we have a negative charge, we're going to add an electron. If we have a positive charge, we're going to subtract the number of electrons. Next thing is that we're going to draw the skeleton, meaning we're going to connect all the atoms together, right? And then with our leftover electrons, we're going to add lone pairs to the outermost to make sure that they fulfill the octet. And then if we have any left over, they'll go on the central atom. And then we have to make sure that our central atom also obeys the octet. So if we have leftover electrons, they would just go as a lone pair. But in the off chance that we're out of electrons, you would take some of those lone pairs on the outside and make them into bonds. And hopefully we have some practice here. So draw the structure for CH4. And so this is the way we do it, right? So carbon has 4 valence electrons. Hydrogen has 1, but it's CH4, so we're going to multiply it times 4. Then we add this up and we get 8 valence electrons. All right, next thing we're going to do is we're going to put carbon in the center of the thing, and now we're going to put our 4 atoms around it. Like this. And so now we connect every atom with a bond. So 1, 2, 3, 4. Every bond has 2 valence electrons, so we subtract that from our total valence electrons. All right, we have 0 electrons left over. So this hydrogen here has 1 bond, and in every bond there are 2 electrons. And I know, and you know, that hydrogen prefers to obey the duet rule, right? It doesn't want 8 electrons, it just wants 2. So it has 2 electrons. That hydrogen's good. Since every other hydrogen has 1 bond, that means that each of those hydrogens is obeying the octet rule, or the duet rule, right? Now the carbon in the center has 1, 2, 3, 4 bonds, right? So it has 4 bonds for our carbon. And then each one has 2 electrons, so 4 times 2 is going to be 8 total electrons. It has its full octet. Therefore, carbon is also obeying the octet rule. And this is how we draw our Lewis structure, right? And this was a very simple one. So hopefully that makes a lot of sense. You can always pause the video and just record this and rewatch it, or you can pause it and take down notes. Hopefully you remember how to do this. All right, let's go ahead and continue on. Let's draw the Lewis dot structure for CH2O. This is formaldehyde, and we'll go ahead and give this a go right here. Okay, so we're gonna do the same thing. We have a carbon. So if I turn on the drawing tool, we have a carbon, we have 2 hydrogen, and we have 1 oxygen. Carbon has 4, each hydrogen has 1, and oxygen has 6. So now I'm going to add this up. 4 plus 2 is going to be 6, plus 6 is going to be 12. All right. So now you're going to say, well, which atom did we put in this central part? This is going to take a little bit of practice, but you see how the name is written, CH2O. When you start with carbon, since carbon is our most important element, the atoms that follow it till you get to the next carbon, if there are more carbons, are all going to be connected to that one. So carbon here in the center, oxygen, hydrogen, hydrogen. We are now going to connect them by a bond. So 1, 2, 3. All right, so we now use 6 electrons. Right, so we have 6 left. And now, remember what we said to do, if you remember from way back when, we said we fill up the outside atoms first. So hydrogen has 1 bond, so that's 2. Hydrogen has a bond, so that's 2. Oxygen only has 1 bond, so now we're simply going to put in 2, 4, 6. So now we have used 6 more electrons. We are out of valence electrons. Oxygen has 8 valence electrons. It has 6 from the lone pairs and 2 from the bond. But our carbon only has 6 valence electrons. It doesn't have the full octet. So remember what we do is that we take one of the lone pairs on the oxygen, and then we make it into a double bond. So now I'm going to try and clean this up just a little bit. Carbon double bonded to oxygen, single bonded to hydrogen, and then lone pair on the left, lone pair on the oxygen. So the oxygen has 2 lone pairs, 2 bonds, right, in the form of a double bond. So it has 8 valence electrons. Carbon has 4 bonds. That is 8. Hydrogen still looking good. And this is all we do. And it just takes practice. And you're going to get, this should be coming back to you. We did do a lot of this last spring. Well, it's been almost a year. But hopefully this all makes sense. And this is just how you do it. So go ahead and pause if you want to write this down. And you should be good. All right, so let's go ahead and continue on. So food for thought. How many carbons in this morning compound? So in case you don't know, this is caffeine. And so real quick, just to think about this, if you guys haven't talked about it, I want you to think about, remember I said you're going to learn a way to draw structures that are going to make it simpler. So I want you to think about how many carbons are in this compound. I'm sure you guys have talked about this already, but go ahead and think about it again. All right, now that you have a second look at it, the most interesting thing in carbon chemistry is that since we want to talk about it, and since most of our structures are going to focus on carbon, we have to find a way to write things in a simpler way. So a couple of rules, and I'm sure you guys have talked about this, is whenever you're talking about heteroatoms besides carbon and hydrogen, they always get written out. So you have 4 nitrogens in this molecule, you have 2 oxygens. Those are very clearly written. But wherever a line comes to a point, or where more than one line meets, or a line comes to an end, that's where carbon's at. So you have a carbon here, 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 and here. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8. Caffeine has 8 carbons. So this is how we start doing our shorthand writing for this, right? So this is wherever 2 lines come together, or more than 2 lines, or whenever a line comes to an end, such as for 1 through an 8, that's going to be a carbon sign. All right. Formal charges. Why do we determine a formal charge as a molecular ion? How to determine formal charges? So we want to determine the formal charge because it's a way to make sure that the atoms are obeying the octet rules and that each atom has its ideal number of bonds. As we go through and we look at all of these, we're going to see that atoms, if they have their preferred number of bonds and lone pairs, will not have charges on them typically. And so we're going to see what that means. So Chem involves the study of structure and reactions of organic molecules. And so this is very much a true statement, is that we care very much. And this is something that I brought in when we first talked about Lewis structures, this idea of we care about how things react and why they react. And if we understand the structure of the molecule, if we understand if there are charges, things like that, they're going to make them more reactive or less reactive. And so if we understand these basic concepts, it'll help us predict what type of reactions are going to occur. All right. And so that's basically what's going on. So now, if we go ahead and understand this, make life easier. So knowing about charge distribution, it helps us interpret mechanisms. Basically, mechanisms is something that's going to come up a little bit later in class. It is the actual process in how molecules form, meaning what is actually happening with the valence electrons. All right, so that's why this is important. And it'll help us to understand intermolecular forces. So if you remember, intermolecular means things between 2 or more molecules, things like dipole, hydrogen bond, London dispersion. If we understand those intermolecular properties, remember we can make predictions about their physical properties and such, and also like what their role is in things. So understanding the structure, understanding the charge, the formal charge, really allows us to make a lot of predictions about that. Okay, so charge distribution is important, and it's always the type of compounds. So ionic and covalent are 2 types. So if we think about ionic, right? If you remember, ionic are composed of ions, right? Ions. So remember, in ionic bonds, right, in ionic molecules, when we think about that, we think about just having a complete donation of electrons between a metal and a non-metal. So something like, say, sodium chloride, sodium is going to donate with 1 valence electron. And so now you have a sodium cation, it has a plus charge. And then you have a chloride anion, which now has an extra electron and now has a minus charge, right? And so this is basically the idea that we're talking about, is that when we have these ionic compounds, this is what's going on. There's a difference in charges. Right? So each ion has a full positive or negative charge. In covalent now, remember this is typically between non-metal, or non-metal metalloid, electrons are shared, right? They're not donating them. So this means that usually an atom is going to have a partial charge. Now they could have full charges, but more often than not, if they're neutral, they're usually going to have a partial charge, meaning one atom is going to be slightly negative, one atom is going to be slightly positive, but they're not going to have a full charge, right? So most organic compounds covalently bonded have shared electrons. Electrons rarely shared equally, right? Meaning non-polar is when they share close to equal, and polar is when they are not. And so here we have a couple of molecules, water on top, and you can see the redder the difference is, like the brighter the red, the more dense the electron, the greater the density electron. So you can see in water, example, between oxygen and hydrogen, there's such a huge difference in electronegativity that those electrons are not sharing at all between the hydrogen and oxygen. They're much closer to the oxygen. And if you look at the one below that, that is one called benzene. It's something we did talk about way back when. This is going to come up a lot more often, but you can see here now that again, that electron density is right in the center between all of those carbons, and those are hydrogens on the outside. Okay. So each atom has more or less a plus or minus charge, but it's more of a partial. And charges are usually fractional or difficult to predict, meaning, yes, I know something's more positive, yes, I know something's more negative, but it's really hard to determine, like, well, what exactly is the charge? So chemists need a way to estimate the electron rich in 4 parts of the molecule, right? We can't just say this is an ion. When we're dealing with covalent compounds, we need an actual way to do that. And so now, formal charge is a very, very simple way to do this, right? It reflects the balance between the original number of valence electrons in an atom and the number of electrons an atom owns in the final Lewis dot structure. So this means that when we think about the valence electrons now, we form bonds and lone pairs, how many electrons are actually solely on the atom versus how many are being shared. And this is what this allows us to do. So if we look here, formal charge in NH4 plus, that is ammonium. And so basically, each atom owns half of the bonding electrons. And so now, when we do this, we're just going to think of the idea of what exactly is the charge on this, right? So each atom owns half of the bonding electrons. And we'll come back and do that formal charge. So common number of covalent bonds and lone pairs for selected atoms. So what this means is that when we think about atoms and lone pairs, each atom is going to have a preferred number of bonds, preferred number of lone pairs. That's just really becomes up to us to calculate. Now, you can always sit there and calculate the formal charge anytime if you need to say, look, this is +1, +2, whatever, neutral. But again, it's just practice, right? The more you do, the better you'll understand, the easier it makes sense. And like I told you guys way back when, about a year ago, was the rule to being successful in these classes, these science classes, so the basic idea that don't do something until you get it right, do it until you can't get it wrong. And it's just going to be this idea of formal charges. And so I'm going to do this for ammonium. So NH4, if I was to draw what this is, it's a nitrogen bonded to 4 hydrogens. And we know that it has an overall plus charge. So to figure out the formal charge on an atom, you're going to take the number of valence electrons minus the number of bonds minus the number of lone pair electrons. So if you have a lone pair, that means you have 2, right? That's 2 lone pair electrons. And if your professor teaches you a different way and that way makes more sense, do that way. But let's take a look at hydrogen. Calculate hydrogen first, all right? Hydrogen has 1 valence electron. Here it has 1 bond. And there are no lone pairs, so 0. So 1 minus 1 minus 0 equals 0. That means the formal charge on hydrogen is 0. And so now all of the other hydrogens all have the same connectivity, just 1 bond. So the formal charge on all of those hydrogens are going to be the same. That makes sense. All right, so now we're going to take a look at nitrogen. Nitrogen has 5 valence electrons. You can use the table up here, right? In the 5th column. Our nitrogen has 4 bonds, right? And now it has no lone pair electrons. So 5 minus 4 minus 0 equals, look at that, +1. The charge of my nitrogen is +1. So now, if you add up all of those formal charges on the hydrogen, so 0 plus 0 plus 0 plus 0 plus 0, plus on our nitrogen, which in this case is +1, we see now that the formal charge on our nitrogen +1 is the only atom that has a non-zero charge. So the overall charge for our molecule is +1. And that's what we see in NH4 for ammonia. Hopefully this makes sense, right? And this is something we have gone over before. So if you need to, go ahead and pause before I clear it. I'll write this down. And so now going on to this table, this is a very handy table, and I really do appreciate this. So the way that this table is structured, the way that it says is common number of covalent bonds and lone pairs for selected uncharged atoms. So meaning if the atom has no formal charge, what is its preferred number of bonds and lone pairs? Hydrogen prefers to have 1 bond and 0 lone pairs. Carbon prefers to have 4 bonds and 0 lone pairs. Nitrogen prefers to have 3 bonds one lone pair. Oxygen prefers to have two bonds and two lone pairs. Halogens prefer to have one bond and three lone pairs. I want to note, we very rarely draw the lone pair electrons on halogens. They are there. There are three lone pairs on halogens. So like if we have HCl or CCl, for each of those halogens have three lone pairs. We just really don't think about it. But this is the way that this table is going to fill out. I'll let you guys come up with examples. This is just basically the idea. All right, hopefully that makes sense. I'm going to clear it here in a few seconds. You can pause it if you need it. All right. Let us continue on. So moving on. What is the formal charge on oxygen? So again, let's do this out. So make sure that we're all good. Calculate formal charge, right? It's the number of valence electrons minus the number of bonds that that atom currently has, minus the number of lone pair electrons, right? So lone pair electrons. All right, so oxygen, if you remember, if you go back and take a look, if you need to pause and take a look, has 6 valence electrons. This oxygen has a triple bond, therefore it has 3 bonds. And it has a lone pair, which means it has 2 lone pair electrons, right? We don't count the number of lone pairs, we count the number of lone pair electrons, right? And so don't forget, there's another way to calculate this. And like I said, if your professor tells you another way and it makes sense, do it that way. This is my way. This is what we learned way back when. But 6 minus 3 minus 2 is going to equal positive 1. And so we're going to see now that our oxygen has a plus 1 charge. Therefore, we would pick B. That should be our correct answer. Hopefully that makes sense. Go ahead and write this down. Before I clear it, we'll go on to the next page. By the way, I hope all of you are doing well in time of COVID. Hopefully you guys are still being smart. I know things are still rough, but you know, the good thing is that we have the vaccine coming out. I'm getting my vaccine next week. As an instructor, as a teacher, I am next up on the board. So that's good for me. Keep it up. Right. So what now is the formal charge on carbon in the center, right? So we're going to basically do this. So, oh, yeah, just pause if you want, just to do it on your own so you can get the answer, so you can get the calculation up. Right? So go ahead and do that. Just go back to that. All right. So go ahead and do that for you right now. So the formal charge on carbon is going to be number of valence electrons, 4, right? Minus number of bonds. So 1, 2, 3, 4. And there are no lone pairs, so 0. So the formal charge on carbon should be 0. And it's just that simple. Valence electrons minus number of bonds minus number of lone pair electrons. All right. Go ahead and do that now. And now let us go ahead and continue on the next one. What is the formal charge on the N nitrogen? So we want the N nitrogen. So that means that we are going to do this one here. If it lets me, maybe. We're going to do the formal charge on this one. So nitrogen, again, look at your periodic table. It has a 5 valence electrons. We're going to subtract number of bonds, and it has 1, 2. So it has 2 bonds there, minus 2. Minus number of lone pair electrons. So 1, 2, 3, 4. 5 minus 2 minus 4 is going to equal -1. That means that that nitrogen has a -1 charge. So my answer should be D, right? And again, number of valence electrons for that atom minus the number of bonds minus the number of lone pair electrons, right? And this is the way it goes. So we always make sure that we follow these basic rules, and hopefully it all makes sense. Hopefully you guys are doing great. All right. So now continuing on. Here, this is a nice little table too. It says formal charge on atom. And so basically it's the idea of what is the scenario. So carbon is going to have a negative charge if you have 3 bonds and 1 lone pair. It'll have a neutral charge if it has 4 bonds and 0 lone pair. And it'll have a +1 charge typically if it only has 3 bonds and no lone pair, right? So that's our rule for that. Nitrogen, as we said, is going to be 3 bonds and 1 lone pair. When it has a -1, as we just saw, 2 bonds and 2 lone pair, and then it's going to be 4 bond and 0 lone pair when it's positive. Oxygen, if you remember, was 2 bonds and 2 lone pair when it has this nice happy neutral charge. we just saw the calculation. If it has 3 bonds and 1 lone pair, it's going to be +1. If it has 1 bond and 3 lone pair, it is going to be -1. And our halogens are happy with 1 bond and 3 lone pair, right? And so now this is kind of the weird one. If we have 2 bonds and 2 lone pair, which we very rarely, if ever, see, is that it's going to be a +1, right? So again, we very rarely, if ever, see that. So for our -1, I'm actually trying to think if there's any scenario where we have a -1. And I think the only case would be if we had 0 bonds and 4 lone pairs. So if it was just an ion, like it's a Cl minus, right, or Br minus, it has no bonds, it's just by itself, and it has 4 lone pairs. And this is true for all of my halogens. All right, so these are the different scenarios. These are handy tables, like the one we had earlier. So it'd be something I would fill out if I were you to keep handy. But again, eventually, you're going to do enough of these practice. If you're doing enough practice, that it'll all make sense. All right, so I'm going to clear this now. Give you guys a second. All right, and clear that. Let's keep moving. All right, so heteroatoms are often drawn without lone pairs. So normally when we draw our structures, remember when we drew that caffeine, we got the caffeine molecule. We usually don't include lone pairs, but they are there. But you can figure out how many lone pairs there are based on the charge of the atom, right? That was that last table we filled out. So it wants us to fill in those missing electrons until you can see them without drawing them in, meaning at some point, you guys are going to be so great and so professional and so amazing. I know you're not going to need to draw lone pairs. But for right now, until it becomes second nature, until you guys really get good at it, and if your professor is saying here, you should probably keep drawing them right now. Just because, again, it's practice. All right. Sorry about that noise. Making myself a snack. So I was just using something in the kitchen. All right, so it says here, this is what it wants us to do, is fill in hidden hydrogens and implied lone pairs. So the first thing I'm going to do here is that we'll do these one by one. And the first thing I'm going to do in our top left one is that I'm going to circle the carbons. So carbon, 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 right? So now I'm going to put in the hydrogens. Every carbon, if you remember, wants to have 4 bonds. So the carbon on the outside already has 1. So 1, 2, 3. It needs 3 hydrogens to get to its happy state. This carbon here already has 2 bonds shown, so it only needs 2 more hydrogens. Same thing here, like that. All right, we've now done that. Now our oxygen is missing some lone pair electrons. So it has 1 bond, 2 bonds. So now it's going to need 1 lone pair here and another lone pair. And now that's happy. So now we have drawn all of the hidden lone pairs and bonds. All right, so I'm going to do that for this next one. Here's the lone pairs, and it has 2 lone pairs of nitrogen. This carbon here has 3 hydrogens, and then this carbon here only has 1. All right, and this is what you do. It just takes practice. And I'll go ahead and write these in for these other ones so you guys get good at it, but you have this now. So just remember, the idea of doing that table was to know how many bonds a carbon wants, how many lone pairs each atom needs to have, right? And so now this oxygen has a minus charge. So if you remember, it has a minus charge when you have 1, 2, 3 lone pairs and a bond. So that oxygen has 3 lone pairs and a bond, right? Which it does now. And finally, our last one. This last one looks a little tricky, but I'm going to circle the carbon. You have a carbon here, and a carbon here. There's 3 carbons here. And now each carbon gets, there's this carbon on the left side already has 1 bond, so it needs 1, 2, 3 more hydrogens to have 4 bonds. The carbon in the center has a triple bond to the right and a single bond to the left. That is 4 bonds. Doesn't need any more. It's happy. And then our last one only has that triple bond, so there's a hydrogen coming off here. So that is the hidden hydrogens and lone pairs, right? So just remember, that's what those tables are there for, to help you to remember how many lone pairs and bonds each atom needs. It just takes practice, and I promise you, this is probably one of the skills that you can pick up pretty easily as you practice, and you're gonna get it really, really easy. All right, let's go ahead and clear that off. I wait for a second. All right. Okay, so hopefully that's making a little bit of sense. So the following molecule, right, says whatever this is propanol. And know that from experience. I'm an old man who's done a lot of chemistry. And so it says, contains an oxygen with a formal charge of +4, contains an oxygen with implied lone pairs, contains an oxygen with a formal charge of 0, A and B, B and C. All right, so remember, if an atom or molecule has a formal charge, it has to be drawn into the problem. So since there is no formal charge here, right, that means that there are no formal charges. So C is going to be correct. We're going to say that that's an answer so far that we need. Sorry about that. There we go. So C is going to be good, right? But now we need to draw on there the missing lone pairs, right? So oxygen is going to have 1, 2, right? So it has implied lone pairs, so it's going to be B. So B and C are correct, so E should be our correct answer, right? So here's the trick. If you're ever given a structure that has, it has implied hydrogens or implied lone pairs, if you see no formal charge, that means that that atom is neutral and it has all of the bonds and lone pairs it needs. So in here, this propanol, they didn't draw lone pairs on the oxygen, but there's no formal charge, which means our oxygen is happy, which means it has to have 2 bonds and 2 lone pairs, which we just drew for it. So it had implied lone pairs, it has a formal charge of 0. Therefore, BC should be our correct answer, so the letter E. All right. I think this is a good place to stop for lecture 1. I'm going to upload this to YouTube, which you're going to know. That's how you can access it. And I'm going to do this for the rest of your lectures. I'm going to break this down, and hopefully it'll help. Again, send me questions. I can work through things. But if you can't make it to a live session when I'm recording this, like on Thursday, like we said, if you send me a question, I can answer it to the best of my ability, right? So please feel free to hit me up in my emails. And hopefully you guys are doing well. Hopefully it's making sense. I'll try to catch up on this for week 1. But my goal is to get you through stuff as best as possible. All right, you guys have a good rest of your week, and I will see you all on Thursday. All right, take care, everyone.